Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Virtual IP addresses and subinterfaces are two powerful tools that network professionals use to extend the capabilities of their physical infrastructure. In this episode, titled, we will explore how these technologies provide redundancy, scalability, and logical segmentation within networks. Virtual IP addresses are used to create flexible addressing schemes that can move between devices in a high-availability environment, while subinterfaces allow a single physical interface to support multiple logical connections. Together, they form an essential part of modern network design. The Network Plus certification exam includes objectives that cover both virtual IP addressing and subinterface concepts. These topics often appear in questions related to routing, interface configuration, high availability, and segmentation. The exam focuses on your understanding of the core ideas behind these technologies, not specific configuration commands. You may be asked to recognize where virtual IP addresses are appropriate, identify scenarios that use subinterfaces, or analyze network diagrams showing VLAN routing setups. A virtual IP address, often abbreviated as VIP, is a logical IP address not bound to a specific hardware interface. Instead, it represents an abstract endpoint that can be shared among multiple devices, typically routers or firewalls, participating in a redundancy protocol. Because it is not tied to a physical port, a virtual IP can shift between devices during a failover event. This behavior ensures that services remain reachable even when one piece of hardware goes offline, increasing network resilience and availability. High availability protocols use virtual IP addresses to provide seamless failover. These include standards like Hot Standby Router Protocol, or HSRP, the Virtual Router Redundancy Protocol, or VRRP, and Gateway Load Balancing Protocol, or GLBP. In each case, multiple routers participate in the group that shares a single virtual IP address. One router is elected as the active device and responds to traffic directed to the virtual IP, while others remain in standby role. If the active router fails, another member of the group takes over the virtual IP and continues service. The distinction between a virtual IP address and a physical IP address is important. A physical IP is tied directly to the network interface card on a single device. It represents a specific hardware endpoint and does not move. A virtual IP, by contrast, is assigned to a logical group and may be held by any device within that group depending on current status. This abstraction makes virtual IP addresses ideal for redundancy scenarios because they can shift between physical devices without requiring changes on client systems. Virtual IP addresses commonly appear on default gateway interfaces. In a typical setup, users are configured to use a single IP address as their gateway, which is actually a virtual IP managed by two or more routers. Virtual IPs are also used in clustered server environments and load balancers where multiple back-end systems share a single front-run address for service delivery. In firewall pairs, virtual IPs ensure that external connections remain uninterrupted even if one firewall fails, making them an important element of fault-tolerant design. Subinterfaces are logical divisions within a single physical interface on a router or layer 3 switch. Instead of requiring separate hardware ports for each network segment, subinterfaces allow multiple virtual interfaces to be defined under a single parent. Each subinterface operates independently and can be assigned its own IP address, subnet, and VLAN configuration. This enables a router to communicate with multiple VLANs through a single connection to the switch, dramatically improving efficiency and reducing hardware costs. The primary purpose of subinterfaces is to route traffic between VLANs without needing multiple physical connections. When configured correctly, a subinterface acts as the default gateway for a particular VLAN, enabling devices within that VLAN to communicate with other network segments. This is especially common in environments where inter-VLAN communication is required, but hardware resources are limited. Subinterfaces support logical separation while maintaining connectivity through a single uplink. To allow subinterfaces to function, VLAN tagging is required. This process uses the IEEE 802.1q trunking protocol to tag Ethernet frames with a VLAN identifier. Each subinterface is configured to recognize and respond to a specific VLAN tag. When a frame arrives at the router, it reads the tag, identifies the associated subinterface, and processes the packet accordingly. This tagging system allows one interface to serve as the gateway for many VLANs simultaneously while maintaining traffic isolation. Naming conventions for subinterfaces follow a specific format to differentiate each logical segment. The general structure is the parent interface name followed by a period and a subinterface number. For example, G0/1.10. This indicates that the subinterface belongs to interface G0/1 and is associated with VLAN 10. Although the number used does not have to match the VLAN ID, it often does for simplicity. Logical configurations such as IP address assignment and VLAN tagging are all applied to the subinterface, while physical settings remain on the parent. There are many benefits to using subinterfaces in a modern network. First, they allow more efficient use of router or switch ports, especially in environments with many VLANs. Second, subinterfaces simplify cabling by reducing the number of required physical links between devices. Third, they offer greater scalability because new VLANs can be added by defining additional subinterfaces rather than installing new hardware. This makes subinterfaces a flexible and cost-effective solution for dynamic network environments. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Each subinterface in a router or layer 3 switch configuration is assigned its own IP address, separate from the physical parent interface. This IP address serves as the default gateway for all devices within the associated VLAN. For example, VLAN 10 might be assigned to subinterface G0/1.10 with the address 192.168.10.1. Devices in VLAN 10 use that address to route traffic outside their local segment. This setup allows a single physical interface to act as the gateway for multiple VLANs, each with its own subnet and logical identity. One of the most common design patterns involving subinterfaces is the router-on-a-stick model. In this configuration, a router connects to a switch via a single physical link that is configured as a trunk. This trunk carries traffic from multiple VLANs, and the router uses subinterfaces to route between them. Each subinterface is tagged for a different VLAN, enabling the router to send and receive traffic from all VLANs on the link. This approach is cost-acceptable and easy to manage, especially in small to medium-sized environments where hardware resources are limited. Virtual IP addresses and subinterfaces can also be used together to enhance network resilience and scalability. When a router uses subinterfaces to route between VLANs, assigning a virtual IP to each subinterface allows the gateway function to remain available even during hardware failure. Redundant routers share the same set of virtual IPs, and failover protocols like HSRP or VRRP ensure that traffic continues flowing without interruption. This combination is especially useful in enterprise networks that require both segmentation and high availability. Troubleshooting subinterfaces requires a clear understanding of how VLAN tagging and trunking work. If inter-VLAN communication fails, one of the first things to check is whether the trunk link between the router and switch is configured correctly. The switch port must be set to trunk mode, and the appropriate VLANs must be allowed on that trunk. Next, verify that each subinterface has been assigned the correct VLAN tag, and that the IP addresses match the intended sub. A mismatch in these settings can prevent devices from reaching their gateway or other VLAN. High availability protocols that use virtual IP addresses behave differently depending on the protocol chosen. HSRP assigns active and standby roles, with only the active router responding to traffic directed to the virtual IP. VRRP operates similarly, but allows for simpler configuration and uses a virtual router IDG-LBP, or Gateway Load Balancing Protocol, is more advanced and allows multiple routers to share traffic loads while using the same virtual IP. Each protocol provides redundancy, but the behavior and load distribution vary, which may affect your design choices. Virtual IP addresses are most commonly used in network designs involving redundant routers or firewalls. In these cases, the virtual IP serves as the default gateway for user devices. If the active router fails, the backup router takes over the virtual IP address and the transition is invisible to users. Virtual IPs are also used in clustered application servers where multiple hosts offer the same service. The IP address remain efficient and multiple, and that's important for people often get the same rope pulled to the same. The virtual IP directs client traffic to the appropriate node in the cluster, enabling fault tolerance and load distribution. Subinterface configurations also require consistent switch settings to function properly. The switch port connected to the router must be configured as a trunk, and all relevant VLANs must be defined in the switch's VLAN database. Without proper VLAN tagging and trunk configuration, the switch may drop tagged packets or misroute traffic. It's also important to ensure that the VLAN IDs used in the switch and subinterface configuration match exactly. Any inconsistency can lead to communication breakdowns between segments. On the Network Plus certification exam, you may encounter questions that ask you to identify the correct use of subinfaces or virtual IP addresses in a network diagram. You might be presented with a configuration scenario where traffic must be segmented by VLAN while also requiring failover capability. Understanding the relationships between subinterfaces, VLAN tags, trunk links, and virtual IP redundancy protocols will allow you to recognize the correct setup and identify misconfigurations. Questions may also test your ability to match protocols like HSRP and GLBP to their roles in virtual IP operations. In summary, virtual IP addresses and subinfaces are logical constructs that greatly enhance the flexibility and reliability of modern network architectures. Virtual IPs allow multiple devices to share a logical address for failover and load balancing, while subinfaces enable a single physical port to serve multiple VLANs. Together, these technologies support segmentation, redundancy, and efficient use of hardware. On the Network Plus exam, a solid understanding of these concepts will help you analyze routing designs, troubleshoot VLAN connectivity issues, and select appropriate redundancy strategies. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.